The night the sky itself became a weapon, a thunderbolt fell from a man-made heaven and shattered the fragile silence of London. No aircraft traced its arc, no siren warned the frightened streets. In the darkness, a single screaming line of fire wrote the terrifying future, the first taste of a war with no place to hide. People looked up and saw only a streak of light, a fireball racing faster than sound. A glimpse of the impossible, a weapon born of science and ambition and shadowed by cruelty. They called it the V2, WWII, the second vengeance weapon. To some, it was a triumph of engineering, a bold statement of human ingenuity that defied gravity and expectation. To others, it was a harbinger of death, a machine whose existence was written in blood and terror. In this story, the V2 is both wonder and horror, a bridge between artillery and the stars, a testament to human brilliance entwined with human suffering. Our journey begins on the windswept shores of Peenemünde, on Germany's Baltic coast. Here, in the early 1940s, a group of young engineers worked in secret, huddled over blueprints in test chambers, poring over calculations and diagrams that promised flight where no man had flown before. They were led by Wernher von Braun, a young scientist driven by curiosity and ambition, and a vision that extended far beyond the battlefields of Europe. He imagined a rocket that could rise above the clouds, reach hundreds of kilometers, and deliver destruction with unparalleled speed. He also imagined, though not yet realized, a rocket that could one day leave the Earth entirely. The V2 was no sudden invention. It was decades of accumulated knowledge, a mosaic of physics, chemistry, and mechanical design. At its heart was a liquid-fueled engine, burning alcohol and liquid oxygen, producing more than 25 tons of thrust. The missile's body, 14 meters of cylindrical steel, carried pumps, tanks, pipes, and gyroscopes, instruments designed to guide it along a precise trajectory. As it ignited and rose, it tore through the sky at supersonic speeds, faster than any aircraft, leaving a trail of smoke and fire. Witnesses later described the soundless approach. The missile arrived before anyone could even hear it coming, a ghost of terror streaking through the night. Each test launch was both a triumph and a gamble. Engineers tracked vibrations, fuel flow, and nozzle pressure. The smallest miscalculation could turn the missile into a deadly wreck. Every successful launch represented years of trial, error, and painstaking refinement. Gyroscopes measured rotation, vanes in the exhaust steered the rocket, and accelerometers ensured it followed the intended course. It was a mechanical symphony of precision and power, a device that merged human intellect with destructive force. Yet the V2's story is inseparable from the human cost of its creation. In the Harz Mountains, prisoners toiled in the Mittelwerk tunnels, assembling these rockets under brutal conditions. Starvation, cold, exhaustion, and violence claimed thousands of lives. Engineers worked alongside guards, sometimes unaware, sometimes complicit, as the machinery of science became entwined with cruelty. The rockets that soared into the sky carried the echoes of suffering in their steel skeletons, a grim reminder that technological marvel often shadow ethical compromise. The first operational use of the V2 came in September 1944. Hidden launch sites across Europe sent these missiles hurtling toward London, Antwerp, and Liège. The weapon moved faster than sound. There was no defense, no interception, only the horrifying instant of impact. Buildings crumbled, streets ignited, and civilians ran in panic. While its strategic effect was limited, often missing targets by miles, its psychological impact was profound. The V2 introduced a new form of warfare, invisible, unstoppable, instantaneous. Even as the missile sowed fear, the world outside the labs began to glimpse its potential beyond destruction. The same engines that terrified cities would later power rockets into space. Engineers who survived the war carried the knowledge of propulsion, guidance, and material science into post-war programs. The trajectory of the V2, though forged in conflict, would ultimately chart a course towards exploration and discovery. The story of the V2 is a study in contrasts. It is science and cruelty, ingenuity and terror, ambition and ethical compromise. It is a weapon that taught the world to fear what could fly faster than sound and also a technology that would one day lift humans beyond the bounds of Earth. Its creation demanded vision, precision, and sacrifice, leaving a legacy as complex as the machine itself. Tonight, we open the archives, light the film reels, and hear the echoes of the first engines roaring to life. We trace the path of fire through the night sky, the human hands that built it, and the lives caught in its shadow. From Peenemünde to the launch pads, from theory to reality, this is the story of the V2, a story of fire, ambition, and the terrible brilliance of a machine that changed the world forever.
The Baltic winds carried the scent of salt and iron, rolling across the quiet sands of Peenemünde, where a secret experiment was quietly reshaping the future of warfare and of space itself. Here, far from prying eyes, a small group of engineers worked feverishly, driven by ambition, curiosity, and a vision that seemed impossibly bold. They sketched cylinders and nozzles on drafting tables, measured the smallest vibrations of test engines, and debated the nuances of combustion chemistry deep into the night. Their goal was audacious: to build a missile that could rise higher than any artillery, travel farther than any bomber, and strike with unprecedented speed. At the center of this endeavor stood Werner von Braun. Young, charismatic, and brilliant, he embodied the engineer's unyielding drive, a mind focused on the abstract perfection of physics and mathematics, yet forced to work under the brutal pressures of a wartime dictatorship. In Peenemünde, scientific obsession collided with the machinery of a totalitarian state. Funding, oversight, and political expectations dictated priorities, while the looming threat of Allied reconnaissance and bombing created constant tension. Every calculation, every test had consequences beyond the laboratory. The test stands of Peenemünde were both marvels and theaters of danger. Massive engines roared to life, flames licking the sky, shaking the ground beneath the engineers' feet. Vibration sensors monitored the structures, thermocouples measured heat, and cameras recorded every frame of the fiery ascent. The early tests were far from perfect. Some engines exploded on the stands, sending debris and fire skyward. Others faltered mid-flight, crashing into the surrounding forests. Each failure taught lessons, some small and technical, others stark reminders of the limits of human control over raw energy. One of the key breakthroughs came when engineers resolved the problem of combustion instability. Early engines had the tendency to oscillate violently, tearing themselves apart. By carefully reshaping injector heads, adjusting fuel mixtures, and fine-tuning nozzle designs, they achieved a rhythm, a harmony in which combustion could burn steadily and produce consistent thrust. Another critical innovation was guidance. The V2 relied on gyroscopes and actuators connected to tiny fins and vanes, subtle adjustments capable of steering the missile across hundreds of kilometers. This combination of mechanical precision and theoretical calculation represented a level of engineering sophistication that was almost unprecedented in the 1940s. Secrecy enveloped Peenemünde like a shadow. The site was ringed with fences, patrols, and listening posts. Workers lived under constant surveillance, and any breach of protocol could be met with immediate punishment. Yet despite fear and isolation, creativity thrived. Engineers scribbled calculations by lantern light, testing ideas in the dead of night while avoiding the scrutiny of commanders and spies. The environment was one of paradox, danger and inspiration, terror and triumph, each feeding the other. Allied intelligence quickly caught wind of Peenemünde's activities. Reconnaissance planes circled the Baltic coast, photographing the test stands and cataloging every structure. The potential of a weapon that flew faster and farther than any bombers was alarming. In 1943, Operation Hydra bombed Peenemünde, destroying parts of the laboratory and killing hundreds of workers. The raids forced the program to relocate production to underground tunnels and dispersed sites, scattering personnel and materials. The engineers adapted, continuing their work in secrecy even as the sounds of bombs echoed across the coast. Peenemünde was also a place of human contrast. Young, brilliant scientists worked alongside military officers, guards, and laborers. Yet for many of the latter, life was a struggle for survival. Food was rationed, conditions were harsh, and accidents were frequent. Behind the polished reports and diagrams lay stories of exhaustion, fear, and relentless pressure. The genius of the V2 was inseparable from the human cost of its making. Despite these challenges, the program achieved remarkable results. The V2 evolved from a fragile, unpredictable machine to a missile capable of leaving the ground with precision, guided by mathematics and mechanical ingenuity. Engineers were learning not only how to make it fly, but how to make it fly reliably, under controlled conditions, with repeatable results. The lessons learned at Peenemünde would ripple far beyond the immediate scope of war, laying the foundations for post-war rocketry and space exploration. In the next session, we descend into the dark heart of production, the middlework tunnels where the V2 was built in numbers and where human lives were expended in staggering quantities. Here, the beauty of engineering meets the harshest realities of wartime labor, and the rockets that would terrorize Europe are forged under unimaginable conditions. Peenemünde taught the world to dream and to fear. Middlework would teach it the price of those dreams. Deep beneath the Harz Mountains, hidden from the skies and Allied reconnaissance, a dark chapter of the V2 story unfolded. The tunnels of Middlework were not just a factory, they were a prison, a labyrinth where human lives were weighed against the clock of war. Here, the advanced machinery of rocketry collided with the harshest human suffering, as thousands of forced laborers toiled under brutal conditions to assemble the engines and fuselages that would later streak across Europe at supersonic speeds. The workers came from concentration camps, their days measured in exhaustion and fear. Starvation, disease, and abuse were constant companions. Every step, every weld, every adjustment was done under the gaze of guards, rifles at the ready. Mistakes could be fatal. A single misaligned pipe or loose bolt might result in punishment or death. Yet, amid the terror, the human drive for survival and ingenuity persisted. Prisoners adapted to the grueling schedule, improvising ways to complete tasks under unimaginable pressure, often while their bodies weakened with fatigue. Above ground, Allied bombings forced constant changes in production schedules. The engineers, driven by both ambition and orders from above, refined the assembly lines, trying to increase output despite shortages of skilled workers, raw materials, and the ever-present threat of inspection or attack. The middlework tunnels were an engineering challenge in themselves. Ventilation, lighting, and structural integrity had to be maintained, while the massive V2 fuselages, engines, and fuel tanks were maneuvered along tracks and cranes through tight underground corridors. Each piece of machinery required careful handling. One misstep could destroy months of labor and cost lives. Despite the horrors, the technical accomplishments were extraordinary. Precision was paramount. Gyroscopes had to be installed with micrometer accuracy, pumps aligned perfectly, and fuel lines meticulously sealed. Engineers and supervisors worked alongside prisoners, monitoring tolerances and ensuring that every missile met the rigid specifications required for successful flight. The blend of advanced science and sheer manual effort produced a machine that was revolutionary for its time. Each completed V2 was a testament to ingenuity under extreme pressure, a mechanical marvel forged in a crucible of human suffering. The middlework facility also illustrates the stark ethical contradictions of the era. The same knowledge that enabled engineers to create a rocket capable of leaving the atmosphere was used to prolong human misery. Reports documented the death toll among laborers. Thousands died before the missile ever left the launch pad. Each rocket, in a tragic sense, carried with it the weight of lives lost during its assembly. The V2's technological triumph was inseparable from the human cost. Despite these challenges, production achieved a grim efficiency. Mobile launch platforms were prepared, and rockets were rolled out from the tunnels with chilling precision. Logistics were coordinated to deliver missiles to forests, fields, and hidden pads ready to fire into enemy cities. The sheer scale of this underground operation, fuel lines, mechanical workshops, testing bays, and launch preparations rivaled any surface facility, yet it existed entirely in darkness, underground, shielded from aerial reconnaissance. The psychological strain on engineers and workers alike was immense. For the prisoners, survival was paramount. For the German engineers, the tension lay in achieving perfection in a device of mass destruction. Mistakes could destroy months of work or cost lives, and each success was tinged with the knowledge of the suffering that made it possible. The middlework tunnels were thus a paradoxical place, the cradle of technological genius and a chamber of human tragedy. As production intensified, the V2 evolved. Refinements in engine efficiency, guidance accuracy, and structural integrity were implemented even in the bowels of the mountain. Despite resource shortages and the constant threat of sabotage or collapse, engineers continued to innovate. Lessons learned in test flights and early deployments were fed back into assembly lines, improving the performance of each subsequent rocket. In the next session, we leave the tunnels and examine the V2 itself, its design,
its engine, and the astonishing mechanics that allowed it to defy gravity and deliver destruction at supersonic speed. We will look at how the combination of precision engineering, fuel chemistry, and guidance systems made it one of the most advanced weapons of the 20th century, and how every component was a delicate balance between genius and danger.
The V-2 was more than a weapon. It was a monument to human ambition, a steel leviathan designed to pierce the sky and rewrite the rules of warfare. 14 meters of polished metal stretched upward, a streamlined cylinder bristling with pumps, pipes, and delicate instruments, each calibrated to guide the rocket through the atmosphere with almost impossible precision. Its engine, burning a mixture of alcohol and liquid oxygen, generated more than 25 tons of thrust. When ignited, the roar shook the ground, and in an instant the missile surged upward, leaving a trail of fire and smoke, faster than the speed of sound, faster than any human could react. The genius of the V-2 lay not just in raw power, but in guidance. A network of gyroscopes measured rotation, accelerometers tracked motion, and tiny vanes in the exhaust directed its path with painstaking accuracy. Once launched, it required no human input. Its trajectory was predetermined, calculated with precision and elegance, a dance of mechanics and mathematics in perfect harmony. But precision came at a cost. Every component had to withstand extreme heat, vibration, and acceleration. A misaligned valve or a crack in the fuselage could turn the missile from a technological marvel into a lethal explosion at the launch site. Fueling the V-2 was a delicate and dangerous procedure. Liquid oxygen, a cryogenic substance capable of freezing flesh instantly, had to be carefully poured into tanks alongside highly flammable alcohol. The engineers treated this process with a mixture of reverence and fear, knowing that a small mistake could result in catastrophe. Launch crews trained relentlessly, rehearsing every movement to ensure timing, safety, and accuracy. The rocket had to be prepared, fueled, and fired in perfect synchronization. When done correctly, the V-2 would rise in a brilliant streak of fire, disappearing into the clouds within seconds, crossing the boundary between earth and sky. Failures were common, and each one a lesson. Engines could erupt violently, guidance systems drifted off course, structural failures shredded fuselages. Engineers meticulously documented every outcome, analyzing vibrations, propellant flow, and nozzle performance. Each failed launch informed the next, a constant, iterative process of trial and refinement. In this crucible, the V-2 evolved into a faster, more reliable, and deadlier weapon. The structural design was deceptively simple yet sophisticated. The fuselage was cylindrical, tapering toward the nose, reinforced to withstand extreme aerodynamic forces. Inside, the engine compartment, fuel tanks, and guidance systems were arranged with almost surgical precision. Even minor misalignments could amplify errors during flight. Engineers had to consider weight distribution, center of gravity, and structural integrity simultaneously. The rocket was a careful balance of science and art, a testament to human ingenuity. The launch itself was a spectacle of technical and psychological intensity. Platforms were camouflaged, often hidden in forests or remote fields. Crews worked with meticulous care, checking pumps, valves, and gyroscopes. Once ignited, the rocket leapt skyward in a fiery plume, accelerating beyond visual tracking in seconds. The supersonic speed meant that the missile could not be heard until after impact. Civilian populations in targeted cities experienced only sudden destruction, the eerie silence followed by catastrophic explosion, a psychological weapon as much as a physical one. Even in war, the V-2 hinted at the future of rocketry. Its engines were the first of their kind to carry a payload into the upper atmosphere reliably. The guidance systems demonstrated that precision flight could be achieved without human pilots. Every component, engine, fuselage, and gyroscope, was a building block that would influence post-war rockets and eventually space travel. The brilliance of the V-2 was undeniable, yet inseparable from the terror it unleashed. Its duality, ingenious and destructive, defined the missile, making it one of history's most complex and influential weapons. In the next session, we trace the V-2 in combat, examining its launches against London and Antwerp, the fear it inspired, and the Allied attempts to counter a weapon that defied interception. From the technical marvel to a tool of terror, The V2's journey into history is a story of both science and consequence, a missile that changed the very perception of warfare.
By late 1944, the V-2 had moved from test stands and underground factories to the fields, forests, and secret launch pads scattered across Europe. Mobile platforms rolled through back roads under the cover of darkness, camouflaged with nets and brush. Soldiers, engineers, and crews worked in tense synchronization, preparing the rockets for the first missions against Allied cities. Each launch was a careful choreography, fueling, arming, calculating trajectories, and preparing crews for the instantaneous destruction that would follow. The V-2 was more than a weapon. It was a theater of precision, fear, and relentless human effort. The first targets were London, Antwerp, and Liège. The rockets left the ground with a violent roar, ascending with terrifying speed. In seconds, they crossed the skies at supersonic velocity, beyond the reach of anti-aircraft guns or fighter planes. There were no warning sirens, no approaching shadows, only the flash of fire and the ultimate impact. Buildings shattered, streets exploded into rubble, lives ended in a moment. The V-2 was not accurate by modern standards, but its speed and unpredictability made it a terror unlike any weapon seen before. It carried both physical devastation and psychological horror, a combination that made it uniquely effective in the war for morale. Civilians in targeted cities were unprepared for this new form of warfare. People ran through streets as the first explosions shattered night and day alike. Rumors spread. Some claimed the Germans had invented a secret bomb. Others whispered about invisible artillery that no one could hear. The missile's supersonic speed meant that the impact occurred before it could be detected. The city had only a fleeting glimpse of the threat, and then the aftermath. Panic spread faster than the rockets themselves. Schools, homes, and hospitals were destroyed. Families scattered, and chaos reigned. The V-2 transformed the concept of total war, making every city a potential battlefield, every street a target. From a military perspective, the V-2's strategic value was complicated. Its payload, while devastating, could not destroy industry on a large scale, and the program's immense cost, both in money and lives, raised questions about efficiency. Yet the psychological impact was undeniable. Londoners would later recall that the rockets seemed unstoppable, each impact a proof of technological superiority and the terrifying reach of the enemy. The V-2, more than any bomber or artillery, demonstrated that the sky itself could become a weapon. Allied responses were desperate and innovative. Reconnaissance flights scoured forests and fields for launch sites. Spies and informants tracked movements, hoping to intercept the rockets before they could fire. Bombing raids were planned to target mobile platforms and supply chains. Yet the V-2 was resilient. Its mobility, secrecy, and speed made interception almost impossible. Even as the Allies gained intelligence, launches continued, a testament both to German engineering and the ingenuity of those who operated the weapons under constant threat. The campaigns also revealed the human dimension of the missile program. Crews who launched the V-2 worked in constant tension. Aware of the destructive power in their hands, engineers monitored systems with nervous precision, knowing that a misstep could destroy the rocket, or worse, the team itself. Meanwhile, prisoners in the tunnels below continued to supply parts and assemble components under unimaginable conditions. Each rocket's flight a reminder of the lives spent in its creation. The V-2 was a machine of both terror and tragedy, a duality that shaped its legacy. Even as the rockets rained down, the world began to glimpse their significance beyond war. The propulsion systems, guidance mechanisms, and structural design hinted at a technology that could, one day, carry humans beyond the Earth's atmosphere. The terrifying innovation of the V-2 was a bridge between destruction and discovery, an engineering marvel that challenged both morality and imagination. By the end of 1944 and into early 1945, the V-2 campaign had caused thousands of casualties, destroyed cities, and spread fear across Europe. Yet its operational limitations, production bottlenecks, fuel shortages, and imprecise targeting meant that, strategically, it could not turn the tide of war. Still, the missile's psychological impact and technological significance were undeniable. The V-2 had rewritten the rules of warfare, introducing a weapon that combined speed, power, and invisibility in ways never seen before. In the next session, we followed the collapse of the V-2 program as Allied forces advanced, capturing launch sites, test facilities, and personnel. We will explore Operation Backfire, the race to secure German technology, and how the engineers and their knowledge became pivotal in shaping the post-war world. The end of the war did not mark the end of the V-2 story. It was only the beginning of a new chapter in human history. By early 1945, the tide of war had turned decisively against Germany. The Allies advanced from the west, the Soviets pushed from the east, and the once secret launch sites of the V-2 program were under imminent threat. What had begun as an audacious experiment in Peenemünde and a deadly campaign across European cities was now facing collapse. Engineers, soldiers, and crews scrambled to salvage technology, documentation, and personnel as the network of tunnels, factories, and launch sites became increasingly vulnerable. Middlework, the underground factory where thousands of rockets were assembled, was one of the first to come under pressure. As the Allies approached, production slowed. Forced laborers were evacuated or left behind under horrific conditions, many succumbing to exhaustion, disease, or violence in the chaos. Engineers faced a dual imperative: preserve the knowledge of the program and ensure that as many rockets as possible could be fired before capture. Logistics, timing, and secrecy became a desperate dance as trains and mobile platforms moved missiles and critical components away from the front lines. The Allies, aware of the technological significance of the V-2, launched operations specifically to seize German expertise and hardware. Operation Backfire, conducted by the British, aimed to test and evaluate captured V-2s. Engineers, scientists, and technicians, both German and Allied, worked side by side, documenting designs, examining engine performance, and measuring structural integrity. Every gyroscope, fuel pump, and nozzle was scrutinized. The Allies recognized that the V-2 was not just a weapon of war, but a stepping stone to space. And the urgency to recover the technology was matched only by the speed of the Allied advance. In parallel, the United States and the Soviet Union engaged in a race to secure German scientists. Wernher von Braun and his colleagues were high-priority targets. They had the knowledge to recreate and improve upon the missile, and in the post-war landscape, both superpowers sought to leverage this expertise. Many of the engineers were eventually brought to the United States under Operation Paperclip, while others went to the Soviet Union, contributing directly to their respective rocket programs. The intellectual value of the V-2 extended far beyond Europe's battlefields. It would shape global power dynamics and the dawn of the space race. The collapse of the German military infrastructure meant that operational V-2 launches dwindled. Mobile platforms were destroyed or captured, fuel shortages became critical, and command networks disintegrated under relentless Allied pressure. Launch crews, once confident and coordinated, faced the terror of advancing enemy forces and the chaos of a collapsing regime. Amid this turmoil, the human cost remained stark. Many of the technicians and prisoners who had contributed to the program were abandoned or left vulnerable in the shifting front lines. Capturing the V-2 technology was a monumental task. Allied teams had to transport massive rockets, delicate guidance systems, and sensitive engineering documents to laboratories far from the front lines. Test launches, measurements, and dissections provided invaluable insights into propulsion, aerodynamics, and guidance mechanisms. For the first time, engineers outside Germany could study the engines, observe fuel dynamics, and understand the gyroscopic controls that had made supersonic flight possible. This knowledge would accelerate post-war missile programs and lay the foundation for human spaceflight. The fall of Peenemünde and Middlework also exposed the ethical dimensions of technological progress in wartime. Allied forces encountered the full extent of the human suffering behind the rockets: prisoners emaciated from forced labor, facilities built on lives lost, and evidence of systemic cruelty. The V-2, once a symbol of innovation and terror, became a somber reminder that human ambition without moral restraint can leave indelible scars. Even as the Allies celebrated the capture of rockets and scientists, the legacy of the V-2 was already reaching into the future. Propulsion principles, guidance algorithms, and structural innovations discovered in Germany would become cornerstones of both American and Soviet space programs. The same engines that had rained destruction on European cities would propel humans into orbit decades later. Technology outlived the war,
carrying lessons and warnings alike. The fall of the V-2 program marked the end of its role as a weapon of terror, but it was only the beginning of its historical influence. The knowledge, engineering mastery, and daring experimentation embedded in each missile now belonged to the world. In the next session, we examine the post-war legacy of the V-2, how its technology launched rockets into space, how engineers who once built weapons became architects of exploration, and how the line between destruction and discovery was forever blurred by this remarkable machine.
The guns fell silent, the skies cleared, and Europe began to breathe again. But the story of the V-2 did not end with the war. Its engines, its guidance systems, its very design would leave an indelible mark on history, shaping the future of space exploration and missile technology. The weapon that had once terrified London and Antwerp now became a seed for human ambition that extended far beyond the Earth. In the immediate aftermath of the war, Allied forces meticulously gathered V-2 rockets, blueprints, and the engineers who had built them. Operation Paperclip brought Wernher von Braun and dozens of his colleagues to the United States, where their knowledge would form the backbone of America's rocket programs. Similarly, the Soviet Union absorbed captured technology and personnel into their own missile development efforts. The expertise of the German engineers, honed under extreme conditions and wartime urgency, became the foundation upon which the first intercontinental missiles and orbital launch vehicles were built. The technical legacy of the V-2 is staggering. Its liquid-fueled engines taught engineers how to manage cryogenic oxidizers and highly volatile propellants. Its gyroscopic guidance systems provided early lessons in stabilizing vehicles at supersonic speeds. The structural design, optimized to withstand extreme aerodynamic and thermal stresses, influenced decades of aerospace engineering. In laboratories around the world, V-2 components were tested, analyzed, and replicated. Each rocket was dissected like a complex puzzle, revealing secrets of propulsion, control, and material science that would eventually launch humanity into space. But the legacy of the V-2 is not only technical, it is profoundly moral and philosophical. These rockets were born in cruelty, the middlework tunnels, the forced labor, the thousands of lives lost to achieve technological ends. Engineers and commanders alike faced ethical dilemmas that would haunt them for the rest of their lives. The V-2 became a symbol of both human ingenuity and the dangers of ambition untempered by conscience. It demonstrated that science can be harnessed for creation or destruction, often with tragic consequences. In the United States, von Braun's team worked tirelessly on the Redstone and Jupiter rockets, directly translating lessons learned from the V-2. These early designs would lead to Explorer, America's first satellite, and ultimately to the Saturn V rocket that carried astronauts to the moon. Across the Atlantic, the Soviets used captured V-2s and engineers to develop the R-1, and later the R-7, the missile that launched Sputnik and heralded the space age. The same machines that had once been weapons of terror were now instruments of exploration and discovery. Public perception of the V-2 evolved as well. Where once it had been a specter of fear, it became a case study in the possibilities and perils of technology. Historians and scientists studied its design to understand not only engineering principles, but also the human decisions behind technological development. Documentaries, books, and research papers explored how a single weapon could bridge the worlds of warfare and science, illustrating the complex interplay between human ambition, creativity, and morality. Yet for every triumph, the shadow of the V-2's origins remained. Survivors of the middlework tunnels recounted horror and resilience. Historians documented the lives lost and the moral compromises made. The V-2 stands as a stark reminder that innovation is inseparable from its context. It is not merely a missile, but a story of human choices, the extremes of ingenuity, and the costs of pursuing progress under oppression. The ultimate lesson of the V-2 is dual. It demonstrates the heights of human achievement and the depths of human suffering that can accompany it. Its engines carried destruction across cities, and later, satellites and astronauts across the void of space. Its guidance systems mapped trajectories of terror and exploration alike, and its story continues to echo, reminding us that technology is never neutral. It is shaped by those who wield it and by the society in which it is developed. As we conclude this series, the V-2 emerges as a bridge between worlds,
the weaponized sky of a global conflict, and the limitless expanse beyond our atmosphere. From Peenemunda's test stands to Middlework's shadowed tunnels, from London streets to the moon's orbit, the V2's legacy is a testament to human brilliance, resilience, and the ever-present moral choices that define the use of knowledge. It is a story of fire and flight, of terror and triumph, of destruction and discovery, a story that forever changed the course of history.